fastest, being the smallest memory can help you if more references are satisfied in that level. And this is just because of locality of reference, the property of locality of reference for the programs that we experience here, that having a small memory is going to be referred more than the bigger memory, which is also the slower memory. Okay, so we also discussed about the main questions here that are uh, Walaikum Assalam. We also refer to the main question here that are listed in this particular recap slide. Like if you are having multiple memories, and we know that they are going to be both slow memories and fast memories, but the main idea is that the level which is closer to the CPU, also called as the higher level, is going to be a small one. So it cannot hold every data element which is present in the lower level. So our first question is, how are you going to place the block within that higher level? So we looked at different schemes like direct mapping, set associative, and associative mapping. Once the block is there, how are you going to identify that this is the block that you need? And so there can be different techniques for that. For direct mapping, we're looking at the line first and then comparing the tag. For fully associative, we match the tags in parallel. Then block replacement, because it's a small level, so frequently you are going to change the block from one stage to another, from one memory to another. So what would be your criteria for changing a block? How are you going to replace the block, and which block should come in its place? So all of that was covered in the block replacement question. Then we had that write strategy. What's going to happen if you are going to write to the higher level? How you're going to propagate the same contents, the same data, or the same modifications to the lower levels, right? So we looked at all these 4 questions in the last class, and we started with the 6 basic cache optimization as well. How to optimize the cache, how to get better result for reducing the average memory access time. So our target was what can be the different optimizations to reduce the average memory access time of the whole memory hierarchy, right? So we were only looking at the time parameter. We were not talking about anything else like power or cost or something else. So we looked at 4 of these optimization in the last class, like larger block size. So we saw that if you keep on increasing the block size, initially you are going to get benefit because the compulsory misses are going to go down. But then if your block sizes are too large, then it's going to affect the capacity of the cache, and obviously the cache is going to get full quickly, because it can hold fewer blocks, because you're not changing the size of the cache, only the block size is changed. So that may result in increase in the miss rate later on if the block size is too big. And because that when you're talking about spatial locality, we are saying that the programs are referring items which are close to each other. But if the block size is too big, such that the elements that are coming in the block are too far away, and then you are never going to access them, then bringing those elements in the cache is going to quickly fill the cache without any use. So you're going to see that the miss rates are going to increase again. So this gives us a bathtub kind of graph, where we have initially we are going to get some reduction in the miss rate, but then we get some increase in the miss rate again if the block size is increased too much. Then we looked at larger cache size. Obviously, this is the easiest thing to do. If you have cache sizes, if you are going to increase the cache size, then obviously more data can come in. But the problem here is regarding power. But since we are not discussing power, so this optimization is obviously going to reduce the average access time. And we looked at higher associativity. So if you are going for a direct map cache, it's better to have a two-way set associative match because the conflict misses reduce in a higher associative cache. Then we looked at reducing the miss penalty. So the fourth and the fifth optimization were reducing the miss penalty. So multi-level caches to reduce the miss penalty means that if you have got not only just two level, if you have an intermediate level in between memory, then those references which were initially going to the memory because they cannot be satisfied in the cache are now going to be satisfied in the middle level, the level between cache and main memory. So that's going to be faster than the main memory, and so many of those references are going to take less time, and this is going to result in reduction in the miss penalty. Right, so let's continue with this. Our fifth optimization is giving priorities to read misses over writes to reduce miss penalty. Again, an optimization to reduce the miss penalty. Right, so we are talking about how can the penalty for fetching a data or block from main memory be reduced if we are talking about. So what do we get with this particular term, giving priority to read misses over writes to reduce miss penalty? Now, the main idea of this optimization is that reads should be completed first. They should be given priority over writes. For this, I want you to have a look at a sequence of instructions. There are three instructions, right? And for that, we have a description of what type of memory system do we have currently. So let's first of all talk about the instructions. What's happening over here? We have a store word and a load word and a load word. So there are just three instructions. The store word is going to store the data at location R0. R0 is a zero register. It's a register which is hardwired 0. So R0's value is 0. Those of you who are not familiar with this, when you are talking about MIPS, the R0 register is a special register which is always 0. So if R0 is used in any reference, then basically we are just talking about 512. Okay, so in the memory location 512, we are going to put the value of R3, right? So this is also shown over here, that R3's content will go to memory location 512. And then the next instruction is load word, which is going to take the value from location 1024 into R1. And then there we have another load word, which is going to take the value of R512 into R2. So there are three instructions over here, right? Now, before going into the detail of these three instructions, I need you to read this. Assume a direct map right through cache. Now, when you're talking about right through cache, this means that when you're going to update, the cache is also going to update main memory, right? And we talked about in the last class that both write through and write back have a write buffer. And what happens in the write buffer is the CPU writes to that buffer and assumes that it has written the same thing to the main memory and can continue on. And when the write buffer is going to see that the main memory is empty, it's going to write the same thing on the write buffer, and it can then remove those entries, right? So assume a direct map right through cache that maps 512 and 1024 to the same block. Now we have the first thing is that it's a direct map cache. And when you're talking about a direct map cache, a block has just one single line to come, right? And here we are assuming that both the block number 512 and 1024 are mapped to the same line, right? So only one of them can come to the cache. So, and a forward write buffer that is not checked on a read miss. And then we have a forward write buffer, means we have just 4 entries in the write buffer that is not checked on a read miss. What do we mean by this, that it's not checked on a read miss? That is, if you have encountered a read miss, then you are not going to check whether that data is available in the write buffer or not. So whenever there is a read miss, what's going to happen is you allow that this write buffer should be emptied first. Okay, so will the value in R2, the question is, will the value in R2 always be equal to the value in R3? Now let's come back to our program here. So the question is, will the value in R2 and R3 be equal? Now let's see what's happening over here. So we are putting something in a memory location. So let me just draw it here. So it's better, could be better understood. Okay, so what we are talking about is that we have a memory here. Okay, so that's it's a little difficult to write using a mouse. Okay, so there is a memory here, and so there are two different blocks. The block at 512 and the block at 1024, right? And then we have a cache over here, which is going to map both of them to a single line, right? So both of them are going to map at a single line. Now, here we have said that right through map that map 512 to the same block. So let's assume that initially this cache is empty, right? So let's assume that this cache is empty. So none of them are currently in the cache. Now this is a write operation, store word. Store word is a write operation, so we are going to write the value in this location 512 over here in the memory. So we have different options. One is write allocate and one is write no allocate. Now what happens in write allocate is you bring the block over here and then you write the block in the cache, right? So in write allocate, you are going to first of all bring that. If it's a miss, if it's not currently in the cache, you are going to bring that in the cache, write it in the cache, and then it depends on what type of write policy do you have. Either you have write back policy or you have write through policy. If you have write through policy, then that same changes are going to happen in the main memory. So what will happen if you don't have this block already in the cache? What will happen, because you have a write through policy? Normally with the write through policy, you can go with write no allocate, right? Or let's say you go with write allocate. So first of all, you're going to bring that block over here. You're going to make some changes, and then there is a write buffer, which is also going to be updated with that changes that the 512 block is going to get the value of R3. And whenever it's going to get time, then it's going to update the same thing in the 512 block. So what happened was that processor ran that particular instruction. It executed that instruction and had stored the value of R3 in cache and also in the write buffer, and had assumed that this value has been written. Okay. Then in the next instruction, what happened is we are loading something from 1024. Now, as we said that both of these blocks are mapped to the same line, this means that 1024 or 512, any one of them can come to the cache. So if the current one is 512 and you want to read something from 1024, you want to bring it in first of all in the memory. Now, if you're going to bring in this block in the memory, it has got no other place other than this particular line. So when 1024 is going to come, what will happen is you are then going to have 1024 over here. The contents of 1024 over here. Now,
Sir, will not override 512?
Yeah, it's going to. So what happened is, if you are going to have a write through policy, then you are going to assume that the same thing was also written in main memory. So you are not going to you're not worried about whether this block could be replaced or not, right? So you use, since you have updated that block and you want another block in the same line, because the write through policy ensures that the same data is available both in the same form in the higher level as well as in the lower level. So the processor is simply going to bring in a new block. Okay, so it's going to bring in the new block and discard whatever was over here, because since it has updated the write buffer, it is assuming that this thing would be written into the memory at some point of time, right? So it has discarded what was over here and this was now replaced by 1024 because of this instruction. This is actually a read miss. This is a read miss because you wanted the block but it's not there in the cache. So that's a read miss. That's an example of read miss, because you wanted this 1024 but it's not in the cache, so you are going to bring it into the cache. So then you are going to read the value of this content and put that in R1. This is what's going to happen. Then
So, sorry, sir, for interruption. Just let me clarify that this 1024 is this buffer box, and the 512 is the cache box. Are you referring to it? This is a cache, and this one is a buffer.
no, actually both of them are main memory blocks. Both of 512 and 1024 are say main memory addresses. So the blocks in which these addresses reside are coming to the same cache line. So this is my cache and this is the main memory. So both 512 and 1024 can occupy only this line. So this
Okay.
means that both of them cannot come simultaneously.
And what about, sir, this 512 and R3, the bottom one?
Yeah, this is a
Uh,
write buffer. This is a write buffer.
right buffer. Okay.
This is a write buffer. We talked about that in the last class, that in a write through policy, one optimization is to use a write buffer. Write buffer is again a small memory which is going to hold the address and the data of whatever is updated, whatever needs to be updated and written to the main memory. So the processor is going to update the cache and it's going to write the same thing into write buffer, and then it's going to assume that it has written that thing to the main memory, although that has not yet been updated. So write buffer is going to look at an appropriate time, and when it feels that the main memory is now not utilized, it's freed for any transfers, then it's going to make a transfer for memory and put the value of R3 or whatever the contents and in that particular location, which was provided to by the processor, right? So what happened in the first instruction was that we updated 512. That update happened in the cache and also in the write buffer, right? But then the very next instruction, we were referring to 1024. So because of this block which has to come into the cache, that block is going to create a read miss, and we are going to get that block from main memory into the cache. So when we do this, anything over here will have to be removed, right? Because any one of them can come over here. And it's easy to remove for the processor because processor has already written that thing in the write buffer. Now what happens in the third instruction? So in the third instruction, we are again loading something from 512 into the cache and storing it into R2. Okay. So what should have happened? What should have happened is you were placing the value of R3 into this location, and after one instruction, you are talking about putting that value, the same value, into R2. So you are not doing anything other than this. You're putting a value in the memory location, getting the same value into R2, right? So that's why we have this question: will the value of R2 always be equal to the value of R3? So this should be the case, right? This should be the case because you are putting the value of R3 into a memory location, and that same memory location is copied into R2. So R3 should be equal to R2, right? But let's see what's going to happen. So now when you have brought in another block, it has replaced that previous content. Now, uh, now the third instruction is also referring to 512, which means that it's going to check the same line, but if it's not going to find 512, this means this is again going to be a read miss. So that third instruction is also a read miss. So this is also a read miss, and we have to bring in the block. And then we are going to bring in 512 into cache. Now is the problem. What value are you going to bring into the cache? That's the main issue, because this value has not been written yet. It's only in the write buffer. That updated value of 512 is in the write buffer currently. There was a miss, and because of that miss, that memory had replaced whatever updates were happened to the 512 block from the cache. So all these updates are no more in the cache, they are only in the write buffer. But the main memory has not been updated yet. So any operation to the main memory, because that's also going to be a read miss, any operation to the main memory is going to actually fetch an older value of 512 because it's not yet been written. Okay, this is what you are assuming. Okay, so is it okay for all of you? Is it okay for all of you? So the question is, will the value of R2 be always equal to R3? So the problem here is, if the write buffer has written the value in main memory, then it's going to be it's going to be equal. But if the value is still in the write buffer and the write buffer hasn't updated the main memory, this means that R3 and R2 are going to have different values. They're not going to have the same values. So the value of R3 is not yet updated in main memories. So if you are going to fetch 512 block again from main memory, which has not yet been updated, so you're going to fetch a different value and you're going to place that value into R2, which is not going to be the value of R3 that you placed 2 instructions ago. Is this clear? Yes, I need some answers from you
Yes,
people.
clear, sir.
Okay.
But so
Yeah.
here one thing that we can say in a manner that both R2 and R3 cannot be equal because both functionalities are different. R3 is in store mode, and the other one R2 is in load mode.
No, actually, what's happening is
The functionality is different. That's why I'm saying that it cannot be equal because
no,
of
no, 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 no,
functionality.
no, no, no. What basically is happening here is, uh, um, say I need to. I'm talking about something like some program is going to put a value of A in memory, and I need to fetch that same location, so I should get A. Right? This is my idea, that if I'm going to load my memory with A, I should get A. This is okay, right?
Okay, sir.
If I'm writing something to a memory location, if I read that same memory location, I should get the same value, right? This is what I need to ask. Now, what's happening over here is just illustrating what problems can occur. What problems can occur if you have a direct map cache. So you're going to put something into the memory, and you have a write through cache, which means that the processor is assuming that if once it has written that the same thing into write buffer, that word would be written eventually in the main memory, and then the processor is going to continue with this operation. It's not going to wait for this write to happen actually in memory. So the second instruction replaced that update from cache, so it's no more there in the cache, it's only there in the write buffer, which is okay. But then in the third equation, in the third instruction, we are looking at the same block. So we are referring to the same block, but it has not yet been written. So if the write buffer has updated the memory before we access this third instruction, before we execute this third instruction, then only we are going to get A again, because that value has been written, and then we are going to fetch the same thing. But if before executing the third instruction, the write buffer has not updated the memory, then you are going to fetch something else, because that data has not been written. And if you're going to fetch again that same block, it would be an older value because the latest value is still in the write buffer. Okay. Now, what I was trying, with these three instructions, the main objective was to illustrate that in such a program, we are basically thinking about getting the same value in R2, which is the value of R3, because if we are going to put something in memory and read that same memory, we should get the same value. But this might not be the case if the write buffer has not updated the memory yet. Okay, so what can be the solution for that? What can be the solution for that? How can we ensure that both R2 and R3 have the same value? One solution for that is that whenever there is a read miss, so whenever there is a read miss, what happens is we always empty our write buffer, because we know that this problem can occur. We know that this problem can occur on a read miss because our write buffers will have some pending updates and it has not updated that yet. So whenever a read miss occur, empty the write buffer. This could be one solution, right? And let's talk about this solution in this case. So if in the second instruction, what we encountered was read miss. So what we are going to do is we are not going to bring in the value of 1024. Rather, we are going to wait for the write buffer to be emptied first, and then we are going to fetch 1024. Okay, so on every read miss, what's going to happen is that you are going to empty the write buffer, right? And then this would ensure that the value that you are fetching from the main memory on a read miss is always going to be updated value. Do you get this point? So if I'm going to update A, but that update has
Sir, one thing, irrespective of the value, whether it is same or not,
irrespective of what
value this 5.2, if instead of 5.2, if we any other value,
any other value on
it
any
should be empty.
on any read miss, we are going to empty the write buffer. This is going to ensure that the main memory is updated, right? So because write buffers are holding pending writes and you are reading from memory directly. So before reading memory directly, you are saying that all those pending writes should happen first, and then I'm going to read so that I get all the updated values, right? Okay.
Okay,
so this is the problem over here. So I'm going to free up some space over here, because if this thing is clear, then I'm going to free up some space on this slide. Okay, so what can be one of the solution? One of the solution is to let the read miss to wait until the write buffer is empty. Okay. Now, what about this solution? If we are going to wait for write buffer to get emptied on a read miss, then it's going to take a lot of time, right? So let's come back to our optimization. And why are we doing this optimization? We are trying to save time, and the main objective of write buffer was to save time. Don't go for the write operations directly to main memory, write them in the buffer. The buffer is going to write them eventually in the main memory whenever it feels that the memory is now less utilized and it can do some operations. So the main idea of write buffer was to help the processor in saving time. But if you're going to wait for the write buffer to be emptied on every read miss, this is going to be too costly in terms of time. But this is a valid solution. It's always going to ensure that R2 and R3 will have the same value. Okay, so this can be one solution. Now the other solution is give priorities to read misses over writes to reduce miss penalty. Now this is the solution that we are going to talk about. How to make this thing better. Or the second solution is check the contents of the write buffer on a read miss, and if there are no conflicts and the memory system is available, let the read miss continue. Now in this second solution, what we are proposing is that if you have got a write buffer which is going to be a small buffer, say for example in this buffer we had just 4 entries, and it's going to store an address and the data of the location where you are going to store. So for example 512, on location 512 I need to update something. So that data is available over here, and that address is available over here. So my earlier solution was that whenever there is a read miss, because this is also a read miss, this is also a read miss. So whenever there is a read miss, we are going to empty the write buffer first, and then we are going to fetch the block. So this means that you are going to empty your write buffer quite frequently. Emptying the write buffer means you're writing to the memory, and writing the memory is a costly operation in terms of time. So you're going to write everything back into the memory. This is going to take a lot of time, and CPU is going to wait a lot, right? The second solution is check the contents of the write buffer on a read miss. If there are no conflicts and the memory system is available, let the read miss continue. The second solution is you're going to check the address fields of the write buffer. If there are no conflicts, that is, that particular address is not available in the write buffer, then you are going to let that operation continue. So for example, in this case, if you're going to reach this is going to be a miss. So what we are going to do is check whether 1024 is anywhere here in the address field. If it's not there in the address field, this means there are no pending updates to 1024, so this can continue, right? Previously in this solution, it couldn't continue because we have to empty the write buffer at every time. But this optimization says that you are not going to empty the write buffer at all times. So you are giving read misses priorities over writes. You are not doing the writes first. You are going to fetch the missing part, the read misses from the main memory, and you're giving priorities to read misses over writes, because this first solution is actually giving writes priorities over read, because it's saying that do the writes operation first and then go for the reads. But this solution says that if there is nothing there in the write buffer, you can continue with your reads. But when you come over here and you see that there is a 512 referred, and this is also a miss, and you see that there is still a pending reference in the write buffer for this particular address, then you are going to empty the write buffer first and continue. Okay. So in this case, the second one cannot continue because there are pending writes in the write buffer. So this optimization is just about whenever there is a read miss, check the write buffer. If there is no conflict, if you cannot find that particular address, you can continue. But if you find that particular address, then you have to ensure that that thing is updated first in main memory, and then you're going to fetch it. So we are not going to directly fetch it from the write buffer. This could be one more optimization, but write buffers are not very advanced kind of logic circuit. So what happens is that it's only updating the stuff from one side, from CPU to memory. So it's not bi-directional that you can get the same data also to CPU. That's not possible. So one optimization could have been that if there is a conflict over here, get that data, same data from here to the cache. But this optimization is not talking about that. It's talking about that if you find an address over here on a read miss for the same block, then you cannot continue until that write buffer is emptied, right? So I hope this optimization is clear now. So when we're talking about read misses, in order to ensure that this particular sequence of instruction is always going to perform accurately, we can go with either of these solutions. But the first solution is too costly in terms of time, because for every write miss, we are going to empty the write buffer. And remember, there are going to be many more write misses than read misses, right? Because there are more read operations. So there are going to be more read misses. And for every read miss, if you're going to wait for the write operations to continue first, this means you are giving priorities to writes over reads. But the second solution says that if you are going to check the write buffer first, if you don't find any conflicting address, then this read miss can continue, right? So in this case, this first miss can continue, but once you go and find the same address over here in the write buffer, then this means that you are not going to continue with that, and you're going to wait for the write buffer to first update the main memory, and then you're going to continue, right? Is this okay now?
Yes, sir.
Okay. So we have just 1, 2, 3, 4, 5 students right now. Ms. Shirina was here. She is not yet He has not yet joined. Okay, so yeah, sixth optimization. Now, sixth optimization is avoiding address translation during indexing of the cache to reduce hit time. Now, this optimization is about reducing the hit time. If you people remember when we're talking about miss penalty, miss rate, and hit time, we said that access time is actually a combination of these three parameter. So our average access time is actually about the hit time uh, plus the memory miss rate into miss penalty. So reducing anything, any of these three can result in saving of useful time, and then you can have a less average access time. So this sixth optimization is targeting the hit time. Hit time was actually the time that you are going to take to refer an item from the first level, right? Okay, so we are going to continue with this. So sixth optimization is avoid address translation during indexing of the cache to reduce hit time. Now for this optimization, I need to explain something for before we go for actually what's going to happen. So up till now, what we have discussed was that whenever the processor is going to issue an address, that address is a physical address. It's an address of main memory, and then it fetches. Is there a question in the chat? Uh, okay. Um, um, so up till now, what we are assuming is that we have an address which is referred for the main memory, and you are going to fetch that directly from main memory. Uh, but things are a little different. Why are they different? The things are a little different because these days, whenever we are talking about CPU generating address, they don't generate address as a physical address. They don't generate uh, the main memory address. So what do they generate then? They generate a virtual address. So the CPUs are considering virtual memories in their mind. So every reference in the program is actually a virtual address, and that address has to be mapped to the physical address. Okay, and when you're talking about just having main memory and a hard disk, so every virtual address will have its mapping there, and then after looking at this mapping, you're going to get that data from memory, and then everything is okay. But when you have a cache in between, then the problem comes: how is cache going to know where is this location, where is this particular block situated, because that address is not of the main memory. So what happens is you need a translation in that case. So this optimization is about avoiding address translation. So we are talking about avoid the address translation during indexing of the cache to reduce hit time, because if the cache is going to start translation first, then this means that when we were talking about getting the data, that CPU accessing directly the cache to reduce the hit time, and if you are going to introduce an address translation in between, so for every reference to the main memory, there would be a translation first, then it's going to access the cache, and it's going to take a lot of time, right? So before we go into the sixth optimization, let me just tell you more about what's happening here. So all the program references, every time we are going to write a load instruction, the address is no more a physical address these days. It's always a virtual address. So what's a virtual address? Okay, so what's a virtual address? So yeah, we have 1, 2, 3, 4, 5, 6 students over here. Now all of you 6 students have some roll numbers, right? You can consider your roll numbers as your physical address. Okay, but when I'm going to address you, I really don't access you through your, I don't really talk to you through your roll numbers. Okay, if it's a big class, that's a different thing. But normally what happens is how we address each other is whenever I'm, for example, if I need to ask some question, I will ask you with your name, like for example Yasir or Iqbal, right? So I'm going to uh, ask you with your name. Now, for example, you can consider yourself that you are not going to respond to your name, rather your roll number, because names can be same as well. So you can have two people having the same name as Iqbal. So there needs to be a translation. If I'm referring to Iqbal Aziz, then that particular name would be translated into some roll number, and then you are going to get your roll number, and then you can give me some answers, right? So the same way. Why? Because when you're talking about CPUs, the physical addresses are small, but the virtual addresses, virtual space is quite big. So you can have more addresses. So what we do is we have a virtual address, and we call that virtual because it really does not exist. It's something like, if you have such a big memory, then you can go with all of these details, but you don't really have such big memory. So you take a portion of memory, and you say that, and along with that, you add your secondary storage as well. And you say that all of this is my memory, but actually the secondary storage is actually mapped as into main memory, but it's not the main memory. But you are making the programmer believe that that secondary storage is also part of your main memory, but the main memory is small. Anything that you are going to access on the main memory is going to be small, and if you're going to write your programs which can only occupy that small portion, then you are going to be very restricted. So the programmer is given an illusion that he or she has got a very big space, but actually the main memory space is small. But if you're considering the storage space available, then that space can be enlarged. So we are talking about virtual memory. So all those addresses are basically virtual addresses which have to be mapped into the main memory's physical address, right? And for that, we have some mappings as well. And for that, we use a page table which is going to maintain which particular virtual page number is mapped to a particular physical page number, right? So once we have an address, for example, if this is our address, this address is going to have a page offset part and a virtual page number part, which is shown in red. Now the page offset part is not changed, only the virtual page number has to be mapped to a physical page number, because what happens is that what we are talking about is the same thing that is happening between main memory and cache, but this time we have main memory and secondary storage. So main memory is small, secondary storage is quite big, so you cannot hold everything which is in the secondary storage into the main memory. So again, you're going to do some kind of mapping over here. So that's the mapping over here. So previously we were dividing it into blocks. Here we are going to divide into page, which are quite bigger than blocks, but also have a unique size. So let's say we have a page of 4 kilobytes. So if you have got a page of 4 KB, so a 4 kilobyte page means that you need to have a 12-bit of page offset. So to access anything within that page, so one page over here is going to come into one page space over here, right? And that page is 4 kilobyte space. And the last part, the page offset part, is going to remain same for both virtual addresses and physical addresses. So the only thing is that in secondary storage, we are going to have many more virtual pages. So they are going to get a different page number. That page number has to be translated into the page number where it is actually located in memory, so that you can get that data from main memory, right? So this part has to be translated, and for that we have a page table which is going to maintain that this page is at this location and this page is at this location. So this page table is quite a big structure here. I'm going to come to that. But once it's been translated, what happens is you get a different page number for a virtual number, and then you combine these two to get your physical address, which is then going to be the physical page number plus the page offset, and then you can access memory. Okay, so this is how it happens. This is how it happens. If you're talking about page table, They can be different organization. Like a flat organization, we have one entry per page, and each entry contains the physical page number, indicates where is that located, right? So one entry per page means, let's say we say we have a virtual memory of 4 gigabytes. This is what we are telling to the programmer, that we have got such big space for your program, but actually the main memory is quite smaller, let's say just in megabytes. So you need to translate that. Okay, so 4 gigabyte, a giga is 30, sorry, and we have 4 over here, so this means 2 raised to power 32. Uh, okay, so Yasir is saying that kindly repeat last slide again, as my net got stuck during that. So I'm going to come to the next slide.
Sorry, sir, my net basically got stuck and I couldn't
Okay,
see.
okay.
Sorry for it.
I'll try to do that. Uh, so you are basically talking about this slide here.
Uh, yes, sir. I up to the you're talking about the physical memory will be same and the virtual page number will be different because of different names.
Now
The
you can consider the same thing that we had considered for main memory and cache. You can consider the same thing for secondary storage and main memory, because main memory is not uh, big enough to hold everything which is there in the secondary storage. So what happens is you need some mapping in this case as well. So you're giving the programmer the illusion that the programmer has got a big space to write its program, and it can have many pages that can be utilized as code or data. Actually, your main memory is not that big, so your main program is going to be brought into the main memory at one time. It's going to have a portion of that program in the main memory, but mainly is going to reside in the secondary storage, right? But then there needs to be a translation. Where is it going to be stored, and how is it going to be brought into them, and when which page number is going to occupy a particular physical page number, right? So what we do is divide everything. Instead of blocks, we use the term pages. So you're going to divide the main memory into different pages. So and secondary storage has got then also your same space into pages. So these pages can occupy one of these spaces, right? And then there should be some way to know where is this page currently in the main memory. So you are going to assign some physical page numbers to these. So this is page number 1 or 0 or 1 and 2 and so on. So actually what's happening is that this page number, your virtual page number, is mapped to page number 152 of the memory. So it's going to it's basically residing in page number 152. So if you need to access anything related to that, it's actually there in page number 152. So we need a translation from this virtual address into a physical address. So this page number 152 is going to hold, it's currently holding that particular virtual page, and then you can access that through that offset. So the main thing is that program is going to generate a virtual address. You need a translation. You need to translate that virtual address into a physical address so that you access that in main memory, right? But if you're going to do that translation, it's going to take a lot of time, because you are involving page tables, and page tables are quite big structure that we are going to just see, and it's going to take a lot of time to get that data from the page table into from page table is going to be a big structure. It's going to also be resided into memory, so you're going to get that thing. So in other words, there will be multiple references to memory, so and that's going to be a lot of penalty if that's not found in the cache. So that this means that this structure has to be efficient structure, but every reference that you're taking to memory is actually going multiple times to the memory. and then you get that same thing, and then you're going to refer to that. So if you're using a cache over here, this could be a very big problem, because caches are used to reduce the time, and if translations and everything are involved over here, it's going to take a lot of time. Okay, so I can continue with this, but let's take a small namaz break of 10 minutes, so that we come back and I'm going to start explaining from the page table, how is page table handled, and what can we do, right? So let's take a small break. I'm going to come back at 7:10. Okay.
Okay, sir.